All right, let's pull back the curtain on artificial intelligence. Ever wondered how a machine actually learns? Well, today we're going to break it all down, from a single spark of an idea to a full-blown learning machine. Let's dive in.
It all starts with this really fascinating thought. To build the future of AI, the pioneers in the field, well, they had to look deep inside ourselves. And that inspiration, it came from the most complex and incredible machine we know of, the human brain. On the left, you've got a biological neuron, right? The very thing that builds our thoughts. And on the right, that's our attempt to capture its magic in math and code. This is literally where the story of machine learning begins.
So that's our starting point. Section 1 is all about this incredible connection, this link between biology and technology, how the blueprint of our own minds kicked off a revolution.
So what does a brain cell actually do? Well, at its core, it's a pretty simple messenger. It gets these little electrical signals through its dendrites, it processes them in the cell body, the soma, and if that signal is strong enough, bam, it fires. It sends a brand new signal down its axon to connect with other neurons. It's just receive, process, transmit. Okay, so that's the biology. Super elegant. But how in the world do you turn that into math? Well, that brings us to its digital twin. It's time to meet the artificial neuron. And check this out. You can see the resemblance right away. Scientists created this mathematical model to basically copy the brain cell. The inputs on the right, they're like the dendrites grabbing all the information. That central node is the soma, doing the thinking. And the output, well, that's the axon terminal, passing the final message along.
Now, this little math model, it has a name, the perceptron. So what is it? A perceptron is a mathematical model of a neuron. It's the fundamental single building block of what we call artificial neural networks, or ANNs.
So how does this thing think? It's actually pretty cool. It takes in a bunch of different pieces of info, the inputs, and for each one it assigns an important score. We call these weights. Then it just adds up all those weighted inputs, and if the total signal is strong enough, it fires off an output. It's really just a clever way of weighing evidence to make a simple decision.
Okay, so we've got one artificial neuron. That's a great start. But let's be real, a single neuron can only make a very, very simple decision. To tackle real-world stuff, we need to think bigger. We've got to start building with layers. And this brings up a huge question, right? If one neuron can only give a simple yes or no, how do we get to something complex, like recognizing your friend's face in a photo, or understanding what I'm saying right now?
The answer, just like in so many things, is teamwork. It all starts with just one.
And then they get together and form a team, which we call a layer. Now here's the really cool part. Every single perceptron in this layer is looking at the exact same input data. But, and this is key, each one has its own unique set of weights. It has its own opinion about what's important. So the layer can search for tons of different patterns in the data all at the same time.
And this is where the magic really happens. We stack these layers together. The first layer on the left grabs the raw data. The middle layers, we call them hidden layers, do all the heavy lifting, finding patterns and then patterns within those patterns. And that final layer on the right, it gives us the answer. Stacking them like this creates a deep, powerful network that can learn things way more complex than a single neuron ever could.
But hang on, there's one more secret ingredient we need. It's a concept that gives these networks their true power. Let's call it the nonlinear spark. This spark is something called nonlinearity, and it comes from what's known as an activation function. See, without it, the network is just a fancy calculator doing simple straight-line math. But the real world isn't made of straight lines, right? Activation functions are the secret sauce. They're what allow the network to learn all the messy, curvy, complex patterns that define reality, like the shape of a smile or the sound of a guitar.
And you've got a few different types, each with its own personality. The sigmoid function, for instance. It's cautious. It's great for simple yes or no answers. 10 is a little more flexible, often a good pick for those middle layers. And ReLU? Oh, ReLU is the fast, efficient workhorse that you'll find in most modern networks. They each basically act as a final gatekeeper, deciding if a neuron should fire, and if so, how strongly.
So, we've built the whole structure of the network. We've got the neurons, the layers, the spark. But a structure isn't enough. Now we get to the most important part. How does it actually learn? It all happens through something we call the learning loop.
This diagram really captures the whole process perfectly.
You see, the network takes in some data, it makes a prediction, then it compares that guess to the right answer, figures out how wrong it was, and uses that info to update itself. Learning isn't a one-and-done thing. It's this constant cycle of prediction and correction.
So it all comes down to this two-step dance. First, you have the forward pass. This is where the network takes the data and, using its current settings, makes its best guess. Then comes the magic, backpropagation. The network looks at the right answer, measures how far off its guess was, we call that the error, and then it works its way backward through the entire network, tweaking every single weight just a tiny bit to be more accurate next time.
It's basically trial and error, but on a massive, super fast scale. This whole loop of guess and correct can happen thousands, even millions of times. And with every single cycle, those internal weights get fine-tuned, allowing the network to slowly, gradually get better and better at whatever we've asked it to do. It isn't instant knowledge, it's a slow process of refinement.
And that brings us right back to the beginning. We've gone from the simple elegance of a single brain cell all the way to a complex, layered network that can genuinely learn and adapt. We've deconstructed the how, and now we're left with the really big question of what. If we can build a machine that learns, what should we teach it first?